So we have a specific spectrum of the full spectrum, which will be using it for weather and climate applications. So how we can use this? So basically, we can take our human eye visible, okay, which works between zero point 0.4 to zero point 0.7 micrometers. So we can clearly detect different objects based on the light reflected back by the object, right? So the source of the light is same, the sunlight or any light, like any light, but the reflectance what we receive from the object, and it is detected at human eye with, the differences are there. That is how we can differentiate the objects. Similarly here, the different materials reflect, absorb and absorb different wavelengths of electromagnetic spectrum. Based on this principle, we actually detect the different types of the objects, like snow and ice, which is a very high reflectance. If we see the percentage reflectance, then broadleaf vegetation, it is reflecting, and again it is coming down the signal at about 600 to 800 or 700. Again, after that, it is again increasing. So the signal is high here, about 600 nanometers, 580 to 600. So based on the high peak reflectance of that particular the object or the target, and the reflectance received at the sensor, so we can actually identify from which object we are receiving the radiance. Similarly, dry soil, wet soil, even the soil, the changes in the composition, or the adding the water into the soil, that is adding, if it becomes wet, then the reflectance will be coming down. See this about 5 to 4 in the beginning. So it follows the same trend. So that's how we can differentiate between these two soil. Then turbid water, because of lot of will be absorbed by the turbid water, so very less will be reflected at the higher wavelengths. Then clean water, only at the up to mid visible, remaining later it is coming down. So most depending on the reflectance, we can identify the type of the object, or uh, the what is the target. So in the graph left, compare relationship between percent reflectance. Okay. So now our part is atmosphere, right? Atmosphere, when it comes to atmosphere, the radiation basically comes from the sun to the earth, and it will go back to the sensor, whatever reflected or emitted by the reflected energy or emitted electromagnetic energy through the atmosphere twice. While once it is coming down from the sun to the earth surface, while it is again going back to the satellite, whatever located at the whatever placed at the like at some altitude. So it has to experience two kinds of interaction in the surface, in the atmosphere. So much of the incident energy is absorbed and scattered by gases and aerosols in the atmosphere before reaching the earth surface. So even shortwave radiation, while it is coming from sun to the towards the surface, it will experience based on the types of gases and aerosols, and it will scatter, absorb, such kind of reactions it will experience. Again, while after absorbing by the earth, then it will again reflect back from that surface. So it will again experience the same, but the radiation which is emitted or reflected, it again changes. So the atmospheric correction removes the scattering and absorption effects from the atmosphere to obtain surface reflectance characterizing surface properties. So we will see further a bit what is the meaning of that. Um, so basically, what types of satellites are available? Orbits also, there are different types of orbits. Like one natural, our satellite, one of the satellite, one of our natural satellite, one of our satellite is the moon. So Earth and moon, if we take, so the moon rotates around the Earth. So that's our natural satellite. Similarly, we have in for our applications in our weather and climate, we use polar, non-polar, and geostationary orbits. And what it means, geostationary means it is actually stationary with respect to the target of the Earth or the Earth. So how the Earth is moving or revolving and around the sun and rotating around itself. The satellite, which is located at 36,000 kilometers, does the same thing as Earth. That is why we are calling it as geostationary. And polar and non-polar, polar basically rotate from the pole to pole. Okay. So non-polar again means it is like not exactly from pole to pole with an inclined orbits, with each has a different purpose. We'll also see how we are going to use it. Then what type of energy sources we are going to use? A passive and active energy source. Passive means the already existing natural source like sun. Sun, whenever the light daytime, for example, the light is the energy is coming to the towards the sun, so over the earth's surface, and again that is the natural source, and whatever reflected back or emitted by the earth's surface we are receiving, that is from the passive sensor. And active sensor means our own source. The satellite, the instrument carries own source, and the energy is again transmitted, or and again whatever received back, the changes in the energy. So based on that, we can derive some parameters. That also we will just experience a bit later. And then solar and terrestrial spectra, this we have already discussed: visible, UV, IR, and microwave. Measurement types: scanning, non-scanning, imager, and sounders. There are different types of the sensors, and that receive the radiance in the instrument, which is located at some 300 to 1000 or 36,000 kilometers. And there are different types of resolutions in the remote sensing, that is spatial, temporal, spectral, and radiometric. And this remote sensing, after understanding its basic and also as well as the with the scientific knowledge, we apply in our regular day-to-day weather, ocean color, land mapping, air quality, radiation budget, etc. So these are all regularly we use the remote sensing for these applications in these sectors. So geostationary orbit is basically located at 36,000 kilometers. So, so over the equator, and multiple observations per day, limited spatial coverage, because it is only carrying the 1/3 of Earth, and it won't cover the polar region. That's only limitation. Otherwise, continuously it monitors the Earth at the same location almost. And examples, weather communication. Similarly, if we see the low Earth orbiting satellites, it is from pole to pole, and it is less frequent. Means it will see again the same location on planet Earth based on the type of orbit and at the altitude. Okay, and it's global and near global. Then special polar basically like Landsat, Terra, Meteosat, and like the non-polar is that GPM and ISS space station, etc. And coming to the satellite, the sensors. So as we discussed, there are two types of sensors. So basically, the sun, whatever light is emitted, received at the are received passed through the atmosphere, Earth's atmosphere, and reaching the Earth's surface. And again, whatever it is going back to satellite is the energy modified from received from the sun. So radiant energy is converted to geophysical parameters like temperature, precipitation, soil moisture, etc. Moody's GPM and Grace. There are different derived products. Similarly, active sensors. So satellite itself sends the signal or energy, then it will change based on the type of object, and it is received back at the satellite. So the differences in the energy varies based on the type of object which energy has been hit. So most of the active sensors are operated at the microwave portion of the electromagnetic spectrum. So it will give the opportunity to penetrate the atmosphere under some conditions, and it has the possibility to get the observations both daytime and nighttime. So it has different applications in meteorology and at surface and atmosphere. Examples like altimeter, lidar, and some scatterometer which we'll use, some sounders, missions, like there are different missions, and the activists basically we are using some in the NWP also. So some resolutions. What is the spatial resolution? Spatial resolution is smallest ground area represented 1 pixel in the satellite image. Like describes how much detail we can see in that surface. High spatial resolution means finer details, that is smaller pixels. Like if we have 30 meters resolution means it is only one pixel, right? Means the point between 2 points, the resolution, the difference, the distance is 30 meters. But if some of the sensors work at a very high resolution, like 30-meter image, if you see on the right side of the image, and if we have a high resolution, spatial resolution like 0.65 meters, we can see much clearly the features, characteristics of the features. So basically, cloud structure, small thunderstorm, there are different applications. Depending on the spectral resolution, spatial resolution, we get much clarity of the how much in detail we can see that defined by the spatial resolution of the data. Then spectral resolution. So it depends upon the satellite orbit configuration, sensor. It's all in the design part. Number and width of spectral bands of the sensor. The higher the spectral resolution, the narrower the wavelength range for a given channel or a band. Like if we have the one single spectrum, for example, all visible, 400 to 700 nanometer, only one band. So we can't see much, we can't differentiate. Okay, whatever received at that height, it is a mixture of all the channels. But if we have multispectral, so we can actually divide depending on how much bands we are receiving the energy from. Depending on that, we can differentiate the objects. So typically multispectral image refers 3 to 10 bands, which hyperspectral. Then if we go to hyperspectral, so it's same visible, we can divide into multiple, much more, very ultra means very high resolution. That bands will be like some hundreds or thousands of the wavelengths, which we receive the radiance. So basically, all these are lively we are using today, as on today, for all the applications. Okay. So radiometric resolution, basically ability to detect small differences in the radiation and intensity. So number of brightness levels that sensor can record. So it is in bits we measure generally. So 8-bit, 10-bit, and 12-bit. So it depends on that the energy received. It has that many levels. Okay, like weak clouds, thin clouds, temperature gradients, all that. The radiometric resolution also define the um, so temporal resolution means the again coming back to the same location, what time, how much time it takes, the frequency, like the polar orbiting, some take 100 minutes, some take 1 day, some take 15, 16 days, like that. There are different temporal resolution satellites which are available. Some are always constantly available, but we retrieve the data like every 15, 30 minutes, like geostationary. Okay. So these all the different definitions which we use in the remote sensing and satellite meteorology. And basically, if we come to the solar irradiance spectrum, if we come from different wavelengths and the solar spectral irradiance, uh, so there are different atmospheric gases which actually react to the to the sun's energy or solar radiation which is coming, or the emitted radiation which is going from Earth's surface. So it will interact with the different gases of the atmosphere. Like point 0.6, it is the some water vapor, ozone, then hydrogen means water vapor and oxygen. There are different molecules which will interact with the atmosphere gases, the radiation. So based on the signal or signature, so we derive these parameters. Basically, water vapor, carbon dioxide, hydrogen, all these temperature channels are which we'll use for deriving the temperatures, and as well as the product satellite applications like fog, then snow detection, fog detection, fire detection, and water vapor imageries, etc. So many derived products we use based on the absorption of the gases. And this, and if we see right now, whatever we are using is like geostationary. There are so many geostationary satellites that have been already deployed by different countries. So for India, we have INSAT 3DR and 3DS, and then USA has GUIS East and West. Then Meteosat we have 9 and 10. So Europe and as well as Africa, part of India also covered by Meteosat. Then we have the like China and Himawari, Japanese satellite. So these are all located at 36,000 kilometers roughly. So these are stationary between pole to pole. Between 60 plus or minus 60 degrees with constantly it is monitoring on the Earth's surface or Earth's atmosphere, so that whatever feature, whatever characteristics, whatever we want to monitor, especially for the Earth's environmental monitoring or the meteorological monitoring of the clouds and etc. It is possible because of this continuous monitoring. And we also have the polar orbiting satellites which rotate from pole to pole. So these satellites have two types of sensors. Basically, all the geostation is mostly all of them are the passive sensors, and they have only visible and infrared range the instruments. Okay, on a spacecraft. And if we come to the low Earth orbiting LEO, low Earth orbiting satellites, also called polar orbiting satellites. Polar satellites are low Earth orbiting satellites comparatively geostationary. So some from 300 kilometers to up to 1,000 kilometers, they're placed, and they have the orbit altitude from surface of the center of the Earth to that orbit. So most of the Earth's whatever we are our talk, we are interest is the precipitation, then air quality, and different clouds. These are all different phenomena which occur on the Earth's atmosphere, troposphere. So we have to monitor this and also use it efficiently for retrieving or nowcasting or using in the NWP for improving initial conditions, subsequently for the improving the forecast. So all these satellites data have been used. Mostly the polar orbiting satellites are containing the visible sensor, infrared sensor, and microwave sensors also in this. And the microwave also we have active and passive. All are having the sensors on board the microwave, these satellites. Okay, so if we come to the geostationary, we have imager and sounder. Imager means it is only like a one layer. Whatever it is the signal or whatever radiance it is received, if it is a window channel, it is coming from near to the surface, reaching the satellite. And if it is sensitive to the clouds and all, so for example, infrared, the radiation which is coming from receiving at the satellite sensor is from the top of the cloud. So it will miss all the radiance below the cloud. So like that, these images and the sounder. Sounder also is available like inside GUIs. There are sounders available on the geostationary. So we retrieve the temperature and humidity profiles from these sounders and derive some useful products. And the low Earth orbiting satellites also have these sounders. Basically, the ATMS instrument and ATOS basically, it is now ATMS. So we have both the temperature and humidity sensitive channels which are flying on low Earth orbiting satellites. And also we have the hyperspectral, that is CRIS and IIAC sensors in the infrared spectrum. So to derive very high, much more, for monitoring, we use those data sets and also for NWP applications. And the active sensors, basically, the scatterometry, if we see, the all of the earth, like 2/3 of the earth is covered with ocean, right? So especially the surface winds over the earth, ocean especially, is actually monitored by the low Earth orbiting satellite. That is the satellites. Basically, we have now the Meteosat, Metop B, and Metop C, and we have our whatever ISRO we have launched MOS satellite, that is OceanSat. We have the OceanSat sensor there, and China has two HSCAT sensors. So all are continuously monitoring the sea surface winds and altimetry and all. There are different purpose satellites, and there are some elongated orbits for different purposes. Okay, so all these satellites products are regularly data is received, and all the places, whatever like National Weather Service or NCMRWF, we can say here for NWP centers, and we directly use it NWP, the radiance directly, and the same data IMD also receives, and they also derive the products and use it for nowcasting applications. So geostation, especially the insight imagery, the Mausam that you wrote on IMD website, they give it for public, the whatever right now the present weather conditions, especially the cloud, the whiter regions, basically infrared, if you see thermal infrared, it's a cloud imagery. Okay. Now, satellite utilization and NWP. NWP, just let us go the applications now, step by step. So, NWP basically, initial value problem. We need as many as observations, and coverage should be all the globe coverage. So, the observations, conventional observations, basically monitored by national weather services like IMD, any other country. So, at data sparse regions, like the resolution and the location of the observations. I'm talking with respect to NWP. So NWP runs on a gridded space. So we need the gridded observations. So, but in reality, the observations are, the point observations located at different regions, discrete locations. And so because of scarcity and the coverage, poor coverage by the conventional, the satellite data will replace or not replace, I don't say. It is actually compensate and also gives more coverage and gives lot of observations at different channels, visible, infrared and microwave channels, and at for different spectral regions, wavelength regions. Okay, so this data will be integrated into the weather model through a technique called data assimilation. Before that, it will go through a lot of screening, the data quality control check and the bias correction. Then based on the DA, data assimilation, resolution and all, data will be thinned, spatial, temporal thinned. Then it will be integrated with means data assimilation method will be the analysis is generated based on the all observations and the first guess. There here the satellite data plays a very crucial role in the improving the initial conditions. So if we see the spatial coverage of the satellites, see here most of the data, the satellites AMVs. The one of the applications, major applications of geostationary satellites is continuous monitoring of the clouds in the infrared, visible infrared and visible and infrared regions. And visible, we have one type, but infrared we have both temperature and water vapor absorptions. So water vapor and temperature sensitive channels we use, and 6.7 and these channels. So because of that, continuous monitoring of the imageries, monitoring of the clouds, and the data we receive at every 15 minutes or 30 minutes, we have the triplets, and using the triplet and using the genetic algorithm and the methods, we derive the atmospheric motion vectors depending on the drift within the time defined. So we derive the winds. It's not like a level, but it's a layered winds. So low level, mid level, and high level winds, and these are very useful for NWP. The coverage is very good. So the second type is radiances. So radiances, again we have discussed the microwave sensitive like EIATMs and some channels, they have full coverage, even some penetrate through clouds also. So it's like a full coverage, it's one day. And there are different satellites. Nova is not there anymore. Now the SNPP and all, Nova 21 and all. Earlier series are all gone. And ASCAT. So I have mentioned that this is an old thing, that ASCAT. So we receive most of these coverage from different scatterometers all over the globe. GPS survey is another technique we use. Using the GPS satellites and low Earth orbiting satellites, the GPS sensor is placed in the low Earth orbiting satellites, and the signal received by the from the GPS satellite and the low Earth orbit satellite. So the delay, because of the atmospheric composition and the water vapor, there is a delay in receiving the signal, and there's a refractivity or the delay. So we measure the delay, use that, there are some products, direct products, temperature, humidity, sounding, and also as well as NWP models, we directly assimilate the zenith delay and the reflectivity. Okay, so all types of sensors, all types of data which will be assimilating in the NWP. So conventional and satellite data I have already discussed. So satellite data gives the more indirect measurement. It's not a direct measurement, but whereas conventional is a direct measurement with a very high resolution, the RSRW radio sound day, its resolution is little bit coarse. Area coverage is very large, but it's a point measurements. So temporal resolution and synoptic, because it's not constant like the conventional observations are synoptic. We measure it every 4 cycles, 0, 6, and 12, 18. UTC cycles are sometimes in between also. And good horizontal coverage with satellite data, whereas conventional poor horizontal coverage. So data volume is very high and low data volumes with conventional. So with this, these are all, the NWP data which have been used, which have NCMWF has been successfully using and assimilating these observations like ATOS, NOVA, these satellites, ATMS, MSR, SSMIS, GMI, and then we have IRC, EIRS, and CRIS. These are hyperspectral, as we discussed. And then we have INSAT 3D, R&S, Imager and Sounder, Severi, then AHI, Himawari, and GUIS ABI. So all these are the geostationary imageries. So satellite winds, we have the full coverage. If we see go to our NCMRWF website and observations and coverage plots, you can see these plots on daily basis, every cycle, whatever the forecast, all the data received at NCMRWF, and we assimilate and create the analysis for other sister organizations also. So here, like AMVs, and these are all scatterometers. The orange is the our OceanSat-3 Indian satellite, and then we have different space-based lidar, which is not available now, but whenever it is available, we have assimilated this. And these are all different geostationary. These are AMVs, these are radiances from the geostationary satellites. Okay, these are all polar orbiting satellites, the coverage, and then insert 3DR the coverage, and GNSS this we have discussed already. And whatever satellite India has been launching, all the data we use in our NCMRWF for improving the initial conditions, all like AMVs from Kalpana, OceanSat-2, then INSAT, Megatropics is a combined mission. SCATSat-1, INSAT 3DR and 3DS, Microsat-2B, OceanSat-3, all the data which we have been assimilating successfully. And whenever satellite, whenever we launch and we do all the quality cut and quality check, and as well as its how good it is in assimilating all these, we derive the statistics, all these AMVs and water vapors and infrared channel radiances, channel imager, the derived wind product AMVs. So based on this, we assimilate in the NWP models. So because of the weighting function, we can get different level the sounding of the radiance and derived products. So because we have large data set, we have in NCMRWF, so we have developed one product. We with our MOS has developed at NCMRWF collaboration with UK Office and IMD a reanalysis called IMDA reanalysis. So if you want to use for your research, so as ERA 5, we also developed for India at a very high resolution, like almost like 12 kilometers spatial resolution, and about 40 years, 1979 onwards. And whenever the satellite era surface, the era has begun, we have been consistently assimilated these observations in our reanalysis. And extra observations also, whatever IMD has all the observations, we have assimilated in the IMDA reanalysis. Okay, we have also checked with respect to background how much it is good. And we suggest you right now this server we are bringing back, so you can start using the data for your research and other applications. We have verified for different the products, daily precipitation for extreme rainfall over Kerala, and this was the portal earlier. I think we are going to incorporate repeat the same, like the data is like MDA is 1 hour and 3 hour pressure level, 1 hour single level, like surface temperature, all the rainfall and all 1 hour. Similarly, we have NGFS 20-year reanalysis for the global at 25 kilometers. So these are all our India developed reanalysis. So people, you can use it the data for your research studies. Then some applications now, let us go through some applications. So importance of satellites, we have already discussed, like coverage of the satellite, and it is a space bound, so we can get continuous observations and there is no interruption. Basically, we are monitoring from the sky, and like it's a tropical region, mostly covered with clouds, and so some the infrared and visible works only daytime, whereas infrared works both day and night. But again, infrared has the limitation that whenever cloud or any object is there, so the radiation which we receive from the below that object, like a cloud, for example, we will miss it. So above that, we will receive. So like that, all the applications, so we can see, and severe weather monitoring. So because of the clouds and the rainfall, heavy estimated rainfall, and monitoring the cyclones, thunderstorms, heavy rainfall, and these are very crucial for early warning or the current status of the meteorological, the phenomena, or the the feature, whatever existing, to know its progress, to monitor continuously. So these satellites are very, very helpful. So this data is integrated for many applications. And then basically, like some special products like cloud top temperatures, as we discussed, like if the cloud is there in the infrared channel, so we can derive the cloud top temperature and cloud top pressure. And water vapor imagery also, the amount of water vapor available in the atmosphere, that will help, to get the clouds, the presence of clouds, or the next progress of the clouds improving, or decay, or weakening of the clouds. That all we can monitor from this. And infrared visible imageries are very useful to detect correctly and monitor uh, the features, the weather systems, basically. So combining all this will provide a very good platform for nowcasting, and also using these radiance data in the NWB applications for improving the weather conditions in initial conditions, for better for generating the forecast, and here correctly monitoring the weather system, and giving a nowcasting like a short range forecast. These satellite data are very, very helpful. So geostationary, polar orbiting, and complementary use, this we have discussed, these satellites. These have been really helping the humanity for precautionary measures, and taking care of any like disaster management, any kind of situations. The satellite derived products are very helpful. So thunderstorms and subsequently the forecast by NWP. So tropical cyclones, heavy rainfalls and floods, heat waves and droughts, all that we can monitor from this imageries and satellite. Early detection, sea surface temperature, and monitoring of and intensification of the systems, because we are tracking continuously the clouds, and also as well as the systems which are like having genesis, or the ocean, especially the cyclones, which will later intensify into cyclones. So those are very, very disastrous. We know, if we know exactly the location of the landfall, or the present situation, what is its intensification, whether it is moving or non-moving, or intensifying or decaying, whether it has possibility to move inland, all that we can see from the space. So we can easily track the system. So there are different tools, with the tools and algorithms which we receive at the satellite level, the reflected radiance. Like we can see that our eyes are visible sensors. Whenever there is some light, our eyes can see and detect different objects, because knowledge we have, that is called the algorithm. So the algorithm actually differentiate the objects. And then the infrared, so the emitted radiation. So our skin is like a infrared sensor. We can feel hot and cold. So similarly, that infrared hot and cold, the sensor can receive, and depend, because the objects are different and they emit radiation based on the object properties. And using the temperature, so we can differentiate the what type of object it is. Like it's a water body, or green, or a snow, or a cloud, or it's a house, like kind of a desert, or different objects on the surface of the planet, surface of the earth. So all that are possible because of the monitoring from the space. And a very good science has been developed, the remote sensing and remote satellite meteorology. So precipitation, especially satellites are there to monitor, especially the tropics. Flood monitoring, SAR, synthetic aperture radar on board some Sentinel-6 and all. Then we have the IRNS also has SAR. So river basins, basically, some are directly we can retrieve the parameters. These are called geophysical parameters. And some what we can do is with the time, because the repeativity is very less. So later, after receiving the data, we can combine all the data and develop the products. So here the direct data is level 0. Level 0 is the raw data set. Then level 1, level 2, level 3. Different products are generated. Level 1 is the radiance geo corrected, which will be going into our NWP models. That is direct brightness temperatures, radiances. Okay. Level 2 is a geophysical parameter like wind, derived temperature, winds, and all those are called level 2 products. And level 3 is combined product. Later time, actually, like using the real-time data, they derive, using all the multi-satellites or all the data sets, they derive a consistent like a data set, like climatological data set like that. So that we will use it for regular model like energy budgets and all, like ISSCP, International Satellite Cloud Climate Research Program. All those data sets also we can use it for monitoring at climate scales. Okay, because the frequency is less, and these are also having applications like agriculture. And we can see, because agriculture, it's not one day sudden growth. So those we can actually monitor like all monthly scale, weekly to monthly scale, seasonal scale, like that. And then river basins, this we have discussed. So because we can detect the clouds and all, so based on that, it can be derived the precipitation and lightning, some lightning. And this is that will actually tells us whether it's a severe weather in the cloud. And let us see another very important cloud cyclone, the phenomena, the weather. Cyclone Amphan, if we see satellite imageries, so if we see continuously, like the life cycle is, uh, like over Bay of Bengal or Arabian Sea, like up to 1 week or up to 10 days. Or, they, because it's a small basin and it will has the genesis with all the parameters, like grace parameters, then it will intensify slowly into a low pressure, depression, deep depression, then cyclonic storm, severe, extremely severe cyclonic, then then super cyclone. So depending on its intensity, the different categorization of the cyclone intensity is estimated, and the severity of the cyclone is based on the intensity. Okay, at what intensity it is going to hit the land, the coast. That is what it is very important. So using satellite, there is one technique developed by Dwarak, so which has been successfully developed, now slightly modified, but still the core theme is the same. Using the satellite imageries, continuous satellite imageries, this technique gives us the T number, like with accuracy of 0.5 to 1 T number max. So the accuracy of this technique is very, very good, based on the central cloud and the basically the cloud, the cloud. We can detect the T number. T number also indirectly tells us the intensity of the system. So depending on the the feature what we detect from the cyclone, T number is assigned, and based on that the intensity is assigned, forecast intensity. Then this method is very, very important for the weather service, national weather service people, if they are using the satellite imageries for detecting the cyclone and forecasting its intensity. Okay. Like for example, if we see, we also have direct broadcast from in India. Like IMD had Delhi, Chennai, Guwahati, and Hyderabad. In IMO is now has one station in Kois, Hyderabad, and one station in NRSC, that is in by ISRO. So NCMDLF receive this data regularly and we use it in the NWP simulation. This is called direct broadcast. Whenever satellite is over our region, we receive the coverage and we derive like the imageries. You see here clearly different stages of the system and how clearly we can see the eye of the system. Okay, so like that we can, these imageries are very useful. These are AVHRR from NOVA and METOP. So again, if we see the microwave, that is like AMSU-A and MHS. So these are all MHS of 5 channels, 1, 3, 4, 5, for example. These are sensitivity to the water vapor. These are MHS again, NOVA 19 and METOP-A. And these are all the AMSU-A temperature channel, channel 2 imageries. So basically, these actually the AVHRR are the visible, which will give you the top of the the cloud, top of the cloud for better. This one, these are AVHRR, right? Only top. We can see clearly the satellite from the satellite picture, the weather feature, the cyclone, very clearly. But what is happening inside at different layers? These will give the like AMSA and MHS, the temperature sensitivity and water vapor 5 channels, the features at that layer. Okay, so with this, the forecasters will get full clarity or the idea on what kind of system and what level the intensity it is there. Okay, so they can estimate and also take the precautionary measure to for the disaster management and etc. All the applications. And some other applications derived by this OceanSat 3. One is that the derived wind, the from IMD or from SAC we receive here directly analysis through source. So we directly assimilate these observations wherever. So whenever any system is there, this it will really help and will be to I detect the system and intensity of the system. Because it is an active sensor, it can penetrate through clouds and will give most of the time 95% it will penetrate. Some very thick clouds, dense clouds, it may miss it. So otherwise, we will get full clarity of the surface winds, sea surface winds. So with accuracy, some accuracy with the limitation, we can get the picture on surface of the earth. And like an OCM, ocean color monitoring, different things. NDVA, sorry, this is NDVA product, the non-measured difference visitation index. So visitation cover wherever it is high, we can derive the visitation index. Then US scatterometer all over the globe, aerosol optical depth, that is the air quality or the dust and all the air quality we can get from the visible channel, this one, the product. So basically the cyclogenesis track prediction SIP, then continuous monitoring of the cyclone and all storm surge forecasting, inundation, because this based on the satellite tracking, so it can actually hit the land, and then based on that how much this inundation, coastal inundation, how much area and with what intensity, it can be estimated using the satellite imageries, satellite data. So like for example, we can get the satellite image and the surface winds overlaid. So we can get the, these are available open platform from Bonidhi portal. You can also see from ISRO. These are publicly available to us. And then air quality, we can see different products, especially, whenever there is a high air quality or the dust or something which is moving, we know clearly using the satellite data from where it is the source from where it is coming and where it is coming. Severe air quality like PM 2.5 and all, we can detect from the satellite images like MODIS and these INSAT 3D or 3DS right now. Let us see some examples from our INSAT, our own Indian satellite, the OLR outgoing long wave radiation. So that will give the in convection over the troposphere, or the convection, how much clouds and all. It is indirect measure of the activity, convective activity. Then in the real time, because we have the infrared imageries, so using thermal infrared 1 and 2 and water vapor channels, we can estimate or derive the QPE, quantitative precipitation estimate. And then sea surface temperature. If we want the SST, we can actually get the data from the window channels. The thermal infrared 1 and 2 is the in window channels. Atmospheric absorption channels, window channels. Okay, window channels means the radiation directly can reach from the surface. It's a window. It's like direct window, and especially the window channels are very useful to monitor the color, ocean color, the and this SST, all these surface things, and these are very helpful. And apart from that, the snow cover, then short-wave infrared, dim infrared channels, and visible channels. Fire, fire, because the temperatures mid infrared and dim infrared channels, we can actually get the differentiate. Then we can get the fire and smoke, aerosol, cloud detection. So all these products are very much derived using these INSAT 3D imageries. Cloud motion vector, this we already discussed. So because of continuously monitoring the globe by the geostationary satellites, so these from this we are deriving the cloud motion vectors using EMV and water vapor and infrared channels. And visible channels also we are deriving some, and water vapor channels. Upper tropospheric humidity using these channels. Fog. So these are all very important for winter nighttime fog. Excuse me. Similarly, sounder. Sounder is like a 18 channels, 19 channel sounder is there. One is visible channel. Geopotential layer precipitable water, lifted index. Main thing is one of the important parameters, lifted index. That is the stability, atmosphere stability parameter. This data is available for public using the MOSDEC. You can log into register in the MOSDEC website, and you can download both imager and sounder, and you can use the data for your research, for research and applications. And maximum some products you can derive using the sounder. Okay. So imager and sounder we have already discussed in the earlier. There's a products only. So there are so land surface temperature, snow, insulation, and energy budget also we derive cloud mask, AOD, rainfall, then OLR. All these products are derived from our INSAT satellite. And these are available for public, these products by IMD website. If you go to the IMD website, then you can see all these products. Because there are many products. Similarly, OceanSat, directly we are getting the winds, then sounder products, and apart from that, we have OceanSat 3. So using that images like stubble burning, smoke, so like because GMI it has the US OceanSat 3. So this also we are deriving. Fog satellite, this also we have discussed the fog and the financial implications of the fog. And let us example, if any, because of the high fog and dense fog, the landing of the flight, very difficult. Many times we hear in Delhi or Western countries, especially Europe, US, many flights have been cancelled. So it is very costly because of the fog. So detection of the fog, forecasting, everything. These are very important, very large financial implications it has. Apart from that, some other application is LULC, land use land cover. We have discussed that very high resolution in centimeter level, or the like in centimeter less than a meter, centimeters level, we can get these products at depending on the type of land surface, whether it is a barren land or a green or a water body or a ocean. It's a whatever types it is. It can we can derive those features from the satellite continuously, and that will help us, to study the changes happened the last 15 years, 30 years, how the land use land cover has changed, how much urban area has been improved or urban area has been developed. All that we can understand those scientific problems using this land use land cover data. And heat wave conditions also, we can actually get something. And heat wave anyway, not heat wave as well. So daily maximum temperature, because LST and all we derive from the imageries, infrared imagery. Land use land cover, aerosol cloud interaction also we can see how much it is. So energy budget. This is one of the important study with this renewable energy, and basically we derive the solar energy, and these this will help us how much insulation we can get, and based on that how much solar energy can be having yield. 60 solar sites energy. So there are different applications in all sectors, energy sector, NWP sector, real nowcasting sector, because all are connected to weather. Weather is direct interacting with the people and in different sectors. So the satellite data has been widely used in the applications of weather and ocean and atmosphere. So using that, these applications are used for different purposes: drought monitoring, rainfall, crop yield, pest outbreaks, climate, long-term planning also it will help, and urban city planning, and whether you want to say agricultural land or barren land, and how much desert is increasing. That all we can see only because of the continuous data available in the from the satellites. So future trends and technologies like high resolution images, we are going ahead. We are going to incorporate AI and develop more and more products. So collaboration and new sensors, which we are in the satellite meteorology developing, like we have lidars and other things that we are going to develop for the future Earth observing system. Part of the Earth observing system, we will be developing new sensors and getting the data continuously and use it for all scales. Right now, from the derived products from nowcasting till the climate scale, like using the satellite data for using of 20 years, 30 years, you can do different studies. Okay, like the convection, the changes in precipitation, etc., etc. All that, these are like real data, and these are very important. So key role: early detection, improving the forecast, cloud cover, remote areas. So saving lives, reduction property damage, faster response, of better forecasting of the weather, and the disaster related weather phenomena, severe weather phenomena. So this will really help agricultural planning also. It is possible here. So conclusion is addressing imageries, so global regional collaboration, this we discussed. So all that using these satellites, that will help in our daily life, everyday life, whether we we are maybe taking one NWP product like weather forecasting from NCMO develop IMD website. You just go and see the wind or precipitation. The data has the satellite data has already gone into the improving the with weather initial conditions, and the forecast is better improved. Okay, so that's how the different applications and how the satellite data in our life, how it helps in the talk we have covered. So with this, I'll be stopping. Dargaji, Dargaji. Thank you all. So any questions, please type your question or you can ask. Thank you. Thank you all.
Thank you, sir.
Thank you so much. Yeah, next, we are developing much more. There are not much changes, but only thing that there are different means there is a data gap. Like only we have particular cycles we are getting the data. Some cycles we are missing, that we are going to incorporate more and more satellites. And observing the weather, three-dimensional weather, that we don't have still many. We will improve that, especially like lidar kind of observations, so that we are going to develop in the next. Because NWP needs, we talk with respect to NWP needs. So that's what the plan is. And mostly like mini satellites, instead of having bigger satellites with more instruments. So mini satellites like cube satellites, like one of the satellite is US-7. So Microsoft to be one of the testing satellite, which worked very well. The satellite, the light-weighted satellites. So maybe upcoming we are planning like that, mini satellites, one sensor. So the cost of the thing is less, and we can send more satellites, so coverage will be more. Such kind of planning we are proposing. No, it is true. That's what I said. Satellite data, it won't tell you anything. It won't tell you temperature. It won't tell you anything. So all the data we are just receiving, like we see with our eye. So our eye receives only the reflected light, because our brain monitor processes that it is a glass, it is a phone, it is a laptop. It detects the object because the algorithm is there. We have already given the known knowledge, the type of the surface. It is a cloud, it is a surface, it is a land, it is a water body. Based on that spectral signatures only, we are using those channels to get the object or the radiance back. So we already have the knowledge. Ground monitoring is the first foremost in the satellite meteorology. Okay. Satellite meteorology is the first we have to validate, and all the algorithms are generated based on the ground truth only. Okay. Thank you.
Sir,
Yes.
actually, one in the chat box there are two questions is available, sir.
Please tell. I don't know.
Uh,
I can't see that.
yeah, what
Okay.
just
Post
to
here
click
the type. Okay.
click in the chat, sir. There one
Chart reply in text.
here in the top corner one chat box is there, na sir.
Chart is there. I opened the chart. I'm seeing the questions and I'm addressing from there only.
Okay.
Some people, Microsoft, it is showing. No, we can't see the chart. No, you can paste here. Otherwise, you can just tell me.
So that only, sir. What upcoming satellites? How
But
confirm that?
already here, I addressed already this.
Oh,
This question is
sure.
addressed.
Then fine.
Thank you. Any other question? Satellite imagery combined with ground-based radar data for more. How can satellite imagery be combined with ground-based radar data for more precise forecast? Forecast, actually it is based on the product. So satellite data is basically the imageries, right? And here ground based is the like a realistic almost. Even ground based radar images are also we are deriving the products right away. Okay. And we have the satellite imageries from the geostationary satellites, and we are also deriving the estimated precipitation QP, quantity estimation precipitation. That both will help together, to detect correctly and also identify the precipitation regions. Like all the clouds will not have the intense precipitation, and also because of the radar, we also know the hydrometeors, what type of hydrometeors and all. So that will enhance the knowledge and also prediction capability to nowcasting or forecasting people. Yeah, that's a good question. Uh, Related to rainfall, information related to rainfall. This is already available. Rainfall, these products, as I discussed, these are available in the IMD website. You please go through. Mosam.imd.gov.in.
Sir, a few questions are there in YouTube channel also.
Okay. You
Sir,
can
how
share
do we,
the chart. Okay, go ahead.
sir, how do we
Hello.
access the NOVA satellite? Sir,
Sorry, I'm
how
not
do we
getting.
access the NOVA satellite? I mentioned that question.
Okay. Okay. So already direct satellite data, maybe derived products you can access from, at the US satellite, I think, access, NOAA, temperature, and um, so from NOAA, I think we can access some data sets. And we have one more thing. What? It's a satellite. Stack. So some Indian satellite data already available from the MoSDAQ website. Okay. So climate data online. The ISCCP available is in the ISCCP website, the cloud data sets. Then the temperature and all. We can download freely the derived products like AIRS and all the derived temperature humidity.
Okay.
From,
You can please share those links, sir. We can share in the Google Drive.
okay, fine.
Yes, sir. And are the data to these websites are accessible freely? Sometimes
Yes,
websites
yes,
are asking
yes.
permission.
No, MoSDAQ is a free. You can download. You can download. You can register and download.
Okay. Okay.
And
And one more.
remaining whatever other satellites also, it is also free for public data.
Okay, okay, sir. And one
Yes.
more question: when ground stations and the station satellite give conflict data for the some locations, how does the physics engine decide which one to trust? Direct ground measurements or a global station average?
No, direct measurements are always, the ground truth is in situ data, right? So in situ only is a correct observation. Satellites, because the satellites based on the spectral resolution and as well as the resolution of the spatial resolution of the imagery. So most of the data we may miss in this. Okay, ground truth always is the correct.
Sir,
How
what is the
Hmm.
basic
Go ahead.
difference between remote sensing and GPS, sir?
Remote sensing and
GPS.
okay. Remote sensing, it is also a remote sensing data basically. It's a technique only. GPS is radio occultation is a technique. GPS is satellite and low Earth orbiting satellites. Using the technique radio occultation, we are deriving the temperature and humidity profiles or directly the refractivity index. We are using it for our applications.
Okay, sir. Okay, thank you very much,
Hello.
sir.
Sir,
Yes.
excuse me. This
Yes.
is
Yes.
Murali.
Go ahead,
So,
Muleji.
yes, sir. Very good evening, sir. I have a doubt regarding air quality, severe air pollution regarding Delhi air quality.
Okay.
So, actually, recently I read an article regarding satellite monitoring of this stubble burning. Like
Mhm.
after harvesting, all the crops will be burned, and for the next seasonal, farming.
Okay.
So, so regarding this one, so many satellite data is missing, sir. Actually, so data
Hmm.
missing is nothing but so what I'm asking is, the stubble burning is more not accurate of this satellite monitoring,
Hmm. Yes.
and due to this one, so
Hmm.
we are not getting the accurate data of this stubble burning.
But
And
Delhi and all already government of Punjab, Haryana, Punjab, those regions, they already know this one about this real true ground truth data they have, because it is a harvesting time and they have to burn all the stubble. And recently even central government also encouraging to take the collect the stubble so that it will be a reduction in the this one, the smoke whatever coming from that region.
yes, yes,
So
flue gases, yes,
that will be, in the future time, maybe there will be alternatives rather than burning. So that's what government is working and planning with different agriculture and all, university also maybe planning on that. This is a big
yeah.
problem during winter, especially over North India.
Yes, 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 sir. Yes,
There is no going,
yes,
right?
yes.
The winds are very weak, and it is only
Yeah.
westerly that time, and
Yes,
we
yes,
have
yes. The
no
westerly
northward
winds are,
movement.
yeah,
So all
yeah.
these basically it is meteorology which is controlling, So if the
Yes,
same
sir.
stubble burning happened today, we don't have problem.
Yes, sir. Actually, so is this required to monitor like manually by some stubble burnings are missing like while burning the actually remote sensing is happening.
Yes, yes. We are, but see, it depends on space resolution because this is like our resolution of inside imagery is 4 kilometer visible, right? But MODIS and all, if we have that imagery, so that we can get 250 meters or up to 1 kilometer. So, but here the agriculture land, the land is not like a full like kilometers. So wherever the imagery, if we have a MODIS like imagery sensor, definitely we can detect like. Such kind of sensors we need. That's it.
Yes, sir.
More
How could be
spatial
the
resolution.
frequency, sir? Like frequency of this monitoring
Frequency,
of
second, MODIS is a polar orbiting. We get only once, twice in a day, one
yeah,
in daytime, one in nighttime. That's why it is difficult to detect. But
exactly, sir.
this fire and all, depending on the nearby pixels, it will be differentiating of the brightness temperatures. We can detect it. So the area and the nearby also has. So it is a mixture. That is why it is
Yeah.
difficult. Your point is correct. So more
Yes, sir.
ground truth is need to be added. But this will also is helping. NRSC, they have developed so many products, and
Yes, sir.
it is
Yeah.
also available on Bhuvan portal. We can also see those real time, I think,
Yeah.
and we can download those images from Bhuvan and all. So that will that's what we were monitoring all types of weather through space from
Yes, sir.
surface, which is not possible.
Yes,
Or
sir.
it is very cost, it is very difficult, or it takes more, human power and all. So we are using alternative, that is space measurements. And using AIML that is already started. So because wherever we are missing some features, AIML, the machine learning algorithms are bringing those characteristics, and
Yes.
that will really help whatever missing with our, algorithms. That will help. That is helping. Yes.
Sure, sure. Thank you, sir. Thank you for
Thank
valuable
you.
insights.
Okay, then thank you all once again. Thank you for attending and listening. I really appreciate all of you. Thank you. Namaste.
Thank you, sir.
Okay.
Thank you. So
Thank you.
thank you to all. We will meet tomorrow in the same time.
Yes, 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 sir. Thank you. Thank you.
So those who are not getting the links, actually what happened, we are lucky to get the links also. So most of the people are listening in the YouTube live only.
Okay.
Okay, sure. Thank you.